So, good morning. Welcome to the first lecture of the course of Carlo Heissenberg. So just a few words to introduce you, Carlo. Carlo was hired at IPhT, Institute of Physics Theory, in 2024. And before being hired, he he obtained his PhD at the Scuola Normale Superiore at Pisa, and then he had three postdocs, Nordita, Uppsala, and Queen Mary, London. Carlo is an expert in quantum field theory, scattering amplitudes, and their application to gravitational waves. As well as, so he's interested in studying the classical limit of scattering amplitudes in order to apply them to the gravitational wave-related observables. But he is also an expert in soft theorems and in asymptotic symmetries, and I will talk a little on these topics in the course. So, welcome.
Thank you, Ricardo. And yeah, let me start by thanking you for having me. And I should start by apologizing because in the last few days I've been a bit under the weather, as you can also hear from my voice. So probably today I will not be operating at 100% efficiency, but yeah, sorry for that. So yeah, as Ricardo anticipated, the idea in this series of lectures is to illustrate a bit some of these recently developed techniques that connect essentially scattering amplitudes and gravitational wave observables. And hopefully, especially towards the end, we will also get to highlighting some connections and the role that some symmetries that emerge at large distances in a sympathetically flat spacetimes have to play in connection with these topics, namely this BMS group. So, as usual with Blackboard talks, it's a bit awkward to present references all the time, so I decided to present these two papers that we have, in particular this review with Paolo and Veneziano, which covers actually a greater part of the material in the first few lectures, and also this other paper with Alessandro. So, especially for the last lecture, and every now here and there I'll also try to provide some more specific references. So yeah, here is the schematic outline of the presentation. The idea for today is to start very slowly, just with some introduction to get everybody on the same page, illustrate a bit the problem you're interested in, more in detail, what techniques have been developed to tackle it. And in particular, today we will start by applying this scattering amplitude strategy by sort of following, let's say, a bottom-up approach, which we will take the incarnation of this elastic exponentiation, elastic iconal exponentiation. Next time, instead we will compare this approach to a different one, which was developed in particular also by David Kosover here at IPhT. So it goes under the name of KMOC due to Kosover, maybe, and O'Connell. And this is a more, let's say, top-down instead strategy. Come up with predictions for gravitational wave observables, and we'll be interested to compare how eventually the two, of course, agree when one gets the right result. And in particular, we will use them, I mean, as a case study to apply them. We will discuss the so-called impulse, so by how much the two scattering objects deflect during a scattering. Then, okay, of course, in the first two lectures, I will introduce some calculations of amplitude that I cannot do on the Blackboard because this takes a computer, and there will be in particular two main difficulties. One, just anticipate a bit, is to come up with the so-called integrand for the amplitude, which you then have to integrate, and this requires calculating some integrals. So I will outsource all the integral calculations to this third lecture. We'll try to explain some of the techniques that can be useful in order to calculate these integrals and come up with the final result. And instead, the last two lectures will roughly be devoted to these applications to radiative effects. So, of course, the problem we are interested in principle, is very easy to state. So let me start with the introduction in a sense. We are going to send into massive objects that interact gravitationally, and in principle, then our job would be to understand what happens. So in particular, they will deflect, or they could even form a merger, so a bound system in which they orbit around each other. In the meantime, of course, they will emit gravitational waves. So we will be interested in studying the properties of the waves that they emit, in particular, not only the waveform itself, so really the signal that will be measured by, that is measured by our interferometry experiment colleagues, but also how much energy and angular momentum is lost by the binary, by the emission, by the interaction with the gravitation. So, and just maybe a couple of more disclaimers, and then we'll stop with the blah blah, the actual part of the course. The first is that I sort of try to organize the material in such a way that is roughly independent from one lecture to another. So if you skip one or two lectures, feel free to come to the next one. It should be reasonably easy to follow. And the second disclaimer is that I had, while having prepared, I had in mind as a main target to say people that are not working on these topics. So the idea is that it should be something pedagogic and introductory to be followed even in the absence of a previous background in these topics. And I apologize to the colleagues who are already experts, but hopefully every now and then I will have managed to include also some material that is of interest to more expert colleagues. And okay, last thing, please feel free to interrupt me at any time, ask questions, and we can make this as interactive as possible. So okay, let me start with the introduction. So, of course, the problem, as stated there, it's very easy to state, but it's very hard to solve, of course, because gravitational interactions are very complicated. So there are essentially two mindsets one can adopt. The first, which is in fact very important for actual predictions that are used by interferometry experiments to come up with the waveform for detection and measurement of gravitational waves, is to just put the system on a computer. And in fact, numerical relativity has been developed to a very great extent, especially after the breakthrough by Pretorius, who managed to simulate the first merger on a computer. Instead, in this lecture, we will try to take a different approach and try to find a small parameter that we can expand in order to make the system tractable analytically. So let me just start by reviewing the analytic approximation schemes that have been developed. In order to do that. So perhaps the most well-known and perhaps also most time-honored one is the so-called post-Newtonian, or PN approximation. This is an approximation in which I will use M when the difference between M1 and M2 is generic. This is a regime in which roughly the size, so the GM over C squared of these objects is small compared to their typical distance, this R over there. And this parameter is small at the same time as the ratio between the velocity, typical velocity of either object, and the speed of light. And just to have an idea, in particular for circular orbit, one can consider this parameter. This is what we usually done in the PN literature, which is, okay, for circular orbit, this is really equal to Gm over R squared. And sometimes it's also useful to express it in terms of the orbital frequency of the orbit. The easy exercise in elementary mechanics to go back to the formula for the centripetal force, etc. You can derive this very easy, but it's also true in general relativity. And you will find by plugging in typical values like that are relevant for interferometry experiments or frequencies of order of a few hertz and masses of the order of say 30 solar masses. If I didn't make any mistake, this parameter is of order 1 over 10. So indeed, it's a good parameter to make a perturbative expansion, this X. And more generally, for quasi-circular orbits, the Viriat theorem ensures that these two parameters are small at the same time. So physically, this means that we are expanding in a regime in which the two objects stay far apart. So the rate between the distance, their size and the distance is small, and also their velocities are small compared to the speed of light. So let's say, as a slogan, this is a weak field and slow motion. Okay. Another regime which is particularly interesting for this approach that we will discuss based on scattering amplitudes instead the so-called post-Minkowski expansion. And here essentially we are going to stay in the regime in which interactions are weak, so this parameter gm over r c squared is still going to be small. But we will not assume generically that velocities are small compared to the speed of light. So in particular, we can stay this hierarchy of space in this form. Smaller, but generically could be a sizable fraction than 1. Of course, it cannot be bigger than 1. And and indeed, this regime is relevant in particular not only for merges but also for scatterings, which, as the title suggests, will be actually the main focus of this lecture. So, let me say weak field, generic velocity. A comment here is that sometimes people say arbitrary velocities, but I will say slightly better to say generic in the sense that it is true that here this parameter can be dialed up and down at will, but as we will see, actually there is an asterisk. So if you take a bit, we will see that this does not actually extend to the true ultra-relativistic limit. So of course, what want to consider the ultra-relativistic limit, we tend to see, or if you want, we tend to 1 because we will soon adopt natural units, which we are more familiar with. But we will see that this is not always acceptable for all observables. In particular, there will be a bound that is dictated by this deflection upward. But let me not anticipate too much. Very good. So, question? Yeah.
Probably a very stupid question. So the first definition is it's slow motion.
Yeah.
Omega is 75 hertz, more or less. So it means what's the interpretation of this orb?
Yeah, the orbital, sorry, orb, I forgot. The orbital frequency.
And then it means that there are 75 times.
Yeah, but still, okay, you didn't make mistakes. It's
Is it possible to have something which is 30 solar masses and it turns 75 per second around? That this is slow motion.
You can check my math for next time.
But it's the mass around which you are orbiting, right? It's a, I think it's a small thing that's orbiting again, around the. Oh.
Yeah, it's really the orbital frequency of the trajectory.
Okay, maybe it's.
Yeah, I mean it's big. It's big, but it's still small compared to the speed of light. If I didn't make this, because of course you have to multiply this by the radius to get the tangential velocity, and then compare with the speed of light. And indeed, how do you say the nu, of course, because experimentalists don't use omega, they use nu, which is omega divided by 2 pi. So. No, sorry. This was actually a distinction which is important. This is the frequency of the gravitational wave, not of the. But okay, but this is just a factor of 2. So let me remind myself. This is twice. This is twice the because. Okay, forgot. But yeah, indeed, this a few hertz, let's say a few tens of hertz for this nu are exactly in the typical range of regions of frequency for our LIGO and Virgo. Yeah.
Oh, okay, because you're considering the late time. Really at the merging, just before the merging.
Well, there is a window. Okay, let me be a bit more precise. There is, as Antoine is saying, but familiar with, there is a regime which these things stay far apart. Is the so-called inspiral, right? Oscillation, and then there is a point in which they merge. So then interactions, of course, at some point become strong because the two things come close together, and so this is what is called sometimes the merger proper or the plunge. Instead, this approximation is valid in spiral. So when these things are still far apart, but of course not too far apart, because otherwise the frequency would be too low, and then it would fall outside the. So I guess what I'm doing here is at the beginning of the spiral, when it comes inside the window of the detector. Very good. So maybe a methodological comment is that besides being interesting because they apply to these regimes, for us theorists, they are interesting because, of course, then one can compare between the two. In fact, I mean, sociologically, as you can imagine, this post-Newtonian approximation is being mostly developed by people who are actually practitioners of GR and developed techniques to solve perturbatively the Einstein equations and the equations for the motions of the object perturbatively in this limit. And instead, this Minkowskian approximation has received a boost after this connection with amplitude was realized. So the two sets of techniques and results that have been developed sort of in parallel, but of course, you should be able to compare them to one another when you re-expand in their common regime of validity. And then you could find agreement between the two. Otherwise, it means that there is a mistake somewhere. And up to now, all these kind of cross-checks, and we will discuss a very simple one later today, have been successful. Some of them in a non-trivial way. And this is sort of a, I mean, boosts our confidence that everything is correct. Before moving to the main part of the lecture, let me also make a comment about some different approximations, which maybe will not play a key role in the lectures, but I think it's good to mention them since we are still in the introductory part. So, as I was mentioning, of course, we are interested in the gravitational wave from this emitted in these processes, and well, the typical frequency of the signal for in particular, we will discuss these scatterings is roughly of order of bidimensional analysis of order v divided by b, the impact parameter. So let me redraw the drawing that I just arranged. So for us, we will be mostly interested in a system in which this is a scattering. So we have particles coming in and then coming out and flying off to infinity. And similarly, now comes the most difficult part of all the lectures, in drawing this rectangle, more or less. So this is supposed to be the impact parameter. This is part of the number 2, and this is part of the number 1. This is what I will refer to as B. This is what I will refer to as Bj. This is what I was calling the impulse. This is the deflection angle. And okay, easy trigonometry exercise. So that this is theta half. So the typical frequency of the radiation emitted during this process is of order v over b. So this we will keep generic in most of our lectures, but it will be interesting to consider the soft limit, which means omega b over v very small. So it's easy to see, again, plugging in values as I did there, that this is not actually relevant for our interferometry experiments, in the sense that this would apply for frequencies that are much below the threshold for actual detection. But it's a very interesting regime because in this, if one focuses really on the low frequency tail of gravitational radiations, there is a set of results that allows us to bypass either the post-Newtonian or the post-Minkowskian expansion, which goes under the name of soft theorems. And this is actually where this connection with the symptotic symmetry, memory effect, and will come about later on in the lecture. So let's say theoretically interesting. And another limit which is very powerful, so again, we will keep the ratio between M1 and M2 mostly generic, but it's interesting to consider the so-called extreme mass ratio limit, in which, say, well, one usually defines this symmetric mass ratio. And this is an interesting regime because, of course, leading order, what happens is that the light object, say M2, moves in the geometry that is produced by the heavy object. So this is leading order, the so-called probe limit, which we all study in elementary GR courses. And then there is actually a technique go beyond this probe limit and expand to higher orders in this mass ratio, which goes in the name of gravitational self-force. I mention this because this is it's been shown to be also a useful organizing principle, for instance, when combined, for instance, with the post-Minkowskian approximation. One of the ideas that have been exploited recently is to organize also the post-Minkowskian expansion, in which one expands in this small parameter, also by powers of this nu, and that's to simplify several issues. Maybe we will touch upon this later on. So, okay, after this sort of longish introduction, let me be a bit more precise about this drawing that I was sketching here. As I was saying, we are considering masses 1 and 2 objects. Most of the time, in this lecture, we will consider them to be non-spinning black holes that, since they stay far apart, will model actually by point particles. Let me come back to this in a second. And the key point is that, although this sounds a bit roundabout at first, we will actually try to use scattering algorithms to describe them. So what we are going to do is that we are actually introducing a new scale. So the regime in which we are going to work is what I will refer to as classical post-Minkowskian scattering. So concretely, this means that we are considering objects and a system such that with the Schwarzschild, the Compton wavelength. Okay, let me try to even include C still for the moment. So roughly the Compton wavelength divided by 2 pi is small compared to the classical size of the curvature that these objects produce. So again, let's say again roughly the Schwarzschild rate. And this is in order to stay in the regime in which the objects actually behave in a classical way, right? So that any interference effect associated with their wave-like nature is very, very suppressed. And then in order to stay in this PM regime, in which again we will require that this is much smaller than the impact parameter, which plays the role of a typical separation. So again, this means that this is the classical regime, and we are in the PM regime. So again, as an exercise, just to have an idea of the scales we are talking about, suppose you indeed calculate this ratio Gm squared over h bar, VC, and check what happens when you plug in these values like 30 solar masses, then you will find that this object is of the order 10 to the 79. So indeed, the classical approximation is very well satisfied for this kind of macroscopic black holes. And okay, the other regime, of course, is we only have observed mergers so far. I can't really give you an estimate for the typical ratio between GM and B, but say again, we can have in mind this estimate we had over 1 over 10. So let's say M over B is roughly of order 1 over 10. So of course we need to go to higher orders in order to have a better approximation for the quantities we are interested in. Okay, so this is the goal. Try to apply some of these scattering techniques to obtain, say, the first few orders in an expansion in this small parameter of some of the key properties of this trajectory under the gravitational wave. Now let me start with some preliminary statements about notations, conventions, etc. So schematic and convention. Just to, if anybody wants to redo any of the calculations at home, knows what I mean. So I'm going to work with this mostly flat method. and in dim red for reasons that will be apparent in a second. Normalization of single particle states from is going to be the following. And I'm going to work with a conventional S matrix, so which we all know and love from our quantum field theory. It is the T-ordered exponential of the integral of the interaction Lagrange, and which we usually write as 1, namely the, well, contribution to the matrix with which nobody interacts with plus IT, which is actually the whole transition matrix sometimes. And amplitudes are going to be for us the T matrix element up to stripping away the momentum conservation delta function. This is what I mean by an amplitude. And here I'm going to adopt this convention according to which all momenta are formally regarded as outgoing, so that's why P alpha plus P beta instead of say P alpha minus P beta. But of course, this only means that for me, the momenta, physical momenta associated with the incoming states are minus the P1, P2, etc., etc. And especially in the first part of the lectures, we will focus on a well, possibly on the simplest amplitude that has to do with this kind of process that must encode some dynamical information about this process, which is a 2-to-2 amplitude, in which the two objects come in, interact, and then come out. Again, P1, P2, P4. So this is the object with mass M1. This is the object with mass M2. And of course, in the scalar case, this is only a function of the Mandelstam invariant. One can build out of this momenta. So we can say it's a function of S and T. Or often as a shorthand, I will just say it's a function of Q, which I will define in a second. So as I said, P1 squared plus M1 squared equal to 0, etc., for the mass shell conditions. Then S is minus P1 plus P2 squared sigma plus M2 squared, and is also equal to what we call E squared. So of course, S is just the energy in the center of mass frame squared. This parameter sigma over there, which, well, in some part of the literature for good reason is also called gamma, is nothing but really the relative Lorentz factor of the two objects. This being the velocity. Whether this is the velocity of particle 1 as seen from the rest frame of particle 2, for instance. And the T is instead minus P1 plus P4. So this is really related to this Q, which is the transfer momentum. So Q mu is equal to P1 mu plus P4 mu is the momentum that is gained by particle 1 during the process. Okay. Just for conventions. So now, as a reminder, especially for students, perhaps one can always define what I was calling earlier as center of mass frame. This means that it's always possible to choose the momenta of the incoming state to be, say, E1 P. Was the drawing that I just erased again? A2 minus P, so in such a way that the spatial momentum, total spatial momentum is 0, and then it's a standard exercise in relativistic kinematics to show that for an elastic process, so that if the masses of the two objects doesn't change, which is what going to happen at the first few PM orders, what can only change is the direction of the momentum. The final state, not say the magnitude, or in particular there is no energy transfer. So P and P prime have the same magnitude. And we call P. And okay, Q in this case, of course, Q is spatial. And also, there is a cute identity which is very useful. So let me quote it: that if E is the total energy, so which is also the square root of the Mandelbrot invariant, then you can say that E times P is equal to M1 M2 times the square root of the sigma squared, being the relative Lorentz path. Okay, just to just to emphasize it, it's obvious from the formula, but of course this goes to 1 in the non-relativistic limit and to infinity in the ultra-relativistic limit. Very good. So the last piece of convention be the following. So let me introduce, in order to be a bit, to make the next equation a bit shorter, introduce a shorthand for this phase space delta function associated with the final state. So it'll be 2 pi delta theta of theta 0. So this is the heavy side theta function. Plus M2 squared pi theta of T4 delta of T4 plus M1 squared. Then by using our definition of amplitude, we can check that the 2 to 2 matrix element we are interested in, P3, P4, as say minus P1, minus P2, again, because these are the minus the physical moment. We can factor out our below momentum constraint delta function and isolate an object which is the object we actually care about, and we call it S of Q, which is just, well, a function, not a distribution, except for this delta function, which is associated to when there is no momentum transfer. So delta Q plus I. Okay, so these are the mass shell constraints for the final state again that I have multiplied. Very good. So up to now this was just bookkeeping. Any questions on this boring part? Okay, so the purpose of all this was just to introduce some notation for this amplitude, which is going to encode some information that we care about. In particular, the objective for today will be to use it to calculate the deflection that is experienced by the object at leading and perhaps leading order if I get there. So the first sort of practical issue that we're facing is that the amplitude is expressed as a function of this transfer momentum. But of course, what we want to do is introduce the impact parameter, which is what we care about, the scattering impact parameter space. So the first thing I'm going to have to do is to go from momentum to impact parameter space, and not surprisingly, this is going to take the form of Fourier transform. So the idea is to consider Fourier transform. So let's do it. All this S of Q over there. And okay, of course, there will be a piece which is just a 1, thanks to the delta function. And then there will be an actually interesting Fourier transform, let me call it FP of A, which now will be a function of B instead of Q. And the definition, okay, it's almost obvious to read it from there, but let's write it. And then discuss it. So now comes about the first simplification in a sense. Remember, B, the impact parameter, was the largest scale in our problem. So we only care about the value of this Fourier transform for large B, which of course by Fourier transform translates to the fact that we can approximate the integrand for small q. This is a familiar mechanism to anyone that has worked with Fourier transforms in their lives. But we will be even a bit more precise about this when we discuss the method of regions in the third lecture. In a sense, it's an application of the method of region. So what is gonna happen is that to leading order we can neglect higher orders in Q of the amplitude, and also possibly these Q squared, because these Q squares are small compared to the P dot Q, simply because this is quadratic and this is linear. So this motivates us to define another Fourier transform, which is a bit simpler, which I will call A tilde, which is sort of the heart of this icon of exponentiation, which means to approximate this sort of complicated delta function, because in principle, these two you can check, essentially constrain the integration to a sphere in momentum space. The idea is to approximate the sphere just by a plane, so neglecting this delta function. Sorry, neglecting these Q squared inside the delta function. And then these delta functions now, which are for linear constraints, simply mean that you are integrating in the plane orthogonal to P1 and P2, which is the transverse plane to the incoming directions. In fact, as an exercise, you can check it either by going to the center of mass frame or by decomposing the two-dimensional momentum as some transverse component plus longitudinal. You can check that these delta functions heal the longitudinal components along P1 and P2, and then you're left with an integration over Q perp, which is D minus 2-dimensional, of course, up to a Jacobian factor, which is here we go. Before going on and applying this strategy to some actual amplitudes, let me perhaps also give you the explicit expression for the typical Fourier transforms that we will need in the case of this 2 to 2 amplitude. As I mentioned, the 2 to 2 amplitude is just a function of S and T, so if you want of E and Q. And then I mentioned that we can expand for small q's, which means that effectively the only type of Fourier transform we'll be caring about, it takes the standard form of a power law, which is the following. P minus 2 Q pair squared to some power nu. And this you can easily evaluate it, say, for instance, going to Schwinger parameters. Squared nu plus 1 minus 1. So these are very easy to do in general, as you can see, and this would be enough, in fact, to perform our Fourier transform in the first part of the course. One last thing before going on. So I said I remember I was neglecting these Q squared up there. Yep.
You don't neglect it with respect to what exactly?
Yeah, let me be a bit more precise about this. So the idea is that small and big are again always with respect to this hierarchy of length scale. So let me set h bar and c equal to 1. And the idea is that by a Fourier transform, this is more than 1 over q. So in this sense, you can see GMQ is small, and also 1 over MQ is sorry, Q over M is small, right? So this in this sense that they are small. For instance, roughly the scale of this P2 will be the energy, so say the mass. So then you see this is roughly mass times Q versus Q squared. And mass is much bigger than Q, so this is in this sense. So precisely about this point, the difference between these two Fourier transforms is non-negligible in general. I mean, when at two leading order they are the same, but in general they differ.
This is simply this small scattering angle.
Yes, indeed. In the end, this scattering angle will be small in this PM expansion, so precisely.
Sorry, the A, the function A of Q orthogonal is not the function AQ with Q equal to Q orthogonal.
Yes,
It is.
it is.
So the equal is approximation.
No, I just use the delta functions. So you.
Okay, it's exact. Okay.
So the idea is that one writes, for instance,
okay.
in a given frame, this will be, say, in the rest frame of particle 1, this will set to 0 Q0, the component along the time direction. And then this other constraint will set to 0 the component along the velocity of particle 2, which is the other longitudinal one. So clearly this will only depend on the other two, say, transverse directions if you are in 4 dimensions. The only slightly non-trivial exercise that leads to you is to derive this Jacobian factor. Easy.
Okay.
Very good. So just wanted to be a bit more precise about this. So it is true that two leading orders are equal, but then there is a correction. What is the first correction? Again, this can be derived. It's a bit of a tedious exercise, so I didn't want to do it on the blackboard, but it's very instructive. One can again either expand generically. So this expansion is, the idea is to introduce some velocities, or maybe dual velocities even. This is slightly easier if they are orthogonal to V1 and V2, but it's the same. And then one has these 4 variables, or one can choose a frame and give an explicit representation, as I was saying. And then one can not only apply this idea to this integral, but also to the one above, and check what the result is. So to leading order, again expanding for small q, of course, you find this 8 but then there is a correction, which is the frame. P dot q perp, and then there is the 1 over 4 p squared. Then you have to introduce an auxiliary variable x, which is to be then set equal to q squared. So now what I'm saying is that I'm regarding the amplitude as a function of q squared rather than q, yeah, scalar. You have to multiply it by this x squared, and then take a derivative, and then set x equal to q perp. So this is the correction that you find. Note that, for instance, just to anticipate a bit, if you have an amplitude that is like 1 over q squared, this correction is simply not there, right? Because then you will get something local. But and the other thing I wanted to emphasize is that this, if you do some power counting again using this hierarchy of scales, you can see that the first correction, so the schematic behavior, this is b times 1 plus h bar over 3 times b squared. So the first correction is going to sub-leading order in the 1 over b expansion. But again, this is a bit of a special feature of the fact that it's only a function of q squared.
Where did the h bar come from?
Yeah, every now and then I will restore it for clarity. Here is just to make it clearly dimensioned, because energy times length is an action. If you set c equal to, I will still set c equal to 1 almost always. So energy and energy and momentum have the same unit, length and time have the same unit, but energy times length, say, it's an action. So it's just the same dimension of h bar. So I'm restoring it by dimensional analysis if you want. Or if you want, it should be sitting here. Well, right? If I will not do it because it's extremely cumbersome to restore it everywhere. Therefore, you have to decide if you also restore it here, probably yes, and then it becomes a mess. But you can always do it at the end, right? Here I'm just saying that the leading order is something, then there is a relative correction, so which must be dimensionless. And since there is a p times b, there must also be an h bar. This is all I'm trying to say. So this is, in a sense, a quantum correction. Very good. So now let's finally, let's try to be a bit more concrete and consider specific interaction for this massive object and derive actually some formula with all this machinery. So as I said, I will consider a minimally coupled scalar. I'm sorry, maybe the question was about the power counting from this formula. I don't know, let's see if I can do it on the spot. So I'm supposed to have x squared divided by p squared, which is, well, I guess, p. And then I have to take a derivative. Oh.
I know, my question was more like usually in the end you do scattering amplitude, but you look in a classical limit that is some of the h bar terms, not all will you drop them. I mean this one.
Yeah, this is the reason why I meant
which never appears.
No, indeed, it doesn't appear as long as you're staying to leading and subleading order in this expansion. As we will see in a second, there is a bit of a mixing between this h bar expansion and the g expansion if one just looks at the amplitude. So this is actually important if one looks, for instance, at the two-loop amplitude. Because, well, I will come back to this in a second, but precisely because this is sub-leading in this h bar. I will come back to this in a second. To leading order is completely negative. For the three level we are going to discuss in a second, this is irrelevant. But sub-leading order it will be relevant in general. Okay, so yeah, let me not bore you too much with the details. The scalar, you all know what these things are. Let me just maybe write down the Feynman rules for them in some gauge, the Donder gauge. Again, in case anybody wants to redo the calculation. So of course there's going to be a propagator. Say this momentum is g. And then there is propagating on the graviton. The momentum is q. Then there is a structure here that I'm going to call U. Maybe writing it down because these symbols sometimes will pop up again in future lectures. So it can be nice to define them anyway. And this P is this combination of etas. And well, since today we are gonna only do the calculation of species at 3 level, we only need one graviton. Prime. Which is going to be minus alpha kappa mu p prime mu plus mu p prime mu minus p mu plus p prime. Well, of course, it could be M1 and M2, and depending on which line. Yeah. Okay, so now what I want to try to do in order to apply this sort of bottom-up strategy I was advertising in the outline is to actually write down the three-level amplitude and see what happens when we perform this Fourier transform. The idea is that this amplitude must know something about the deflection, but up to now it's not entirely clear how to extract it. So let's sort of try to build it as we go. So three levels. So of course in this theory it's very simple. There's only one diagram, this one. And so of course we have to remember that Feynman diagrams calculate the expectation value of IT. So then we have to triple I or multiply by minus I. Then we have to apply the bracket. So I can pull out my convention P. This is Q. So minus I times that minus I kappa. And then there is going to be P1 mu, P4 mu, is 1 mu for mu minus mu 1 dot p4 minus m1 squared. Then there's going to be the propagator joining the two. So minus I p mu over sigma divided by q squared. Please correct me if you see anything wrong, because otherwise it's never going to work. And then p2 p3 p2 rho p3 sigma p3 p2 sigma p3 rho minus p4 sigma p3 plus p2 minus p2 plus.
Could you define kappa somewhere?
Ah, sorry, yeah. For me, kappa is the shorthand notation for square root of h pi t. G is the Newton constant. And in fact, just to be even a bit more precise, of course, you can derive these Feynman rules by the Einstein-Hilbert Lagrangian and minimally coupled scalar action, and then this is going to be expressed in terms of the metric. Of course, the metric we're going to explain it around space-time in this way. But then, in order to include the properly, to have a properly normalized graviton field and have the usual Feynman rules, one has to remember that there is a factor 2 kappa in front of the, and this is the canonically normalized, the canonical field. Instead, this is the dimensionless metric fluctuation that is actually going to be relevant when things are saying defining what LIGO measures.
Is a kappa squared.
Where? Ah, thanks. Yeah. Yeah, minus I. Very good. So now the idea, okay, the factor in front would be a plus. Let me say that I get it right. Minus I, minus I, minus I, minus I. Very good. And then kappa squared. Thanks, Patrick. And then here, let's try to be a bit clever about this instead of just doing all the contraction, otherwise we will never finish. Remember, the idea is that eventually we're going to take a Fourier transform of this with respect to Q, and we only care about long-range contributions, right? So in particular, things that have a long-range tail for in B space. So of course, looking at the formula that I gave you a few minutes ago, anything of the type Fourier transform of Q squared to the 0 or to 1 or to 2 or anything analytic in general will just be localized, right? Because the Fourier transform of, say, a constant will just be a delta function in this space, so we don't care. So we can set it to 0 in this, if we are only interested in the long range. So you see, anytime these contractions give something that cancels this 1 over Q squared, we can just throw it away. So for instance, here, we have P1 plus P4, which is Q minus P1. Okay, minus Q squared. The minus M squared cancels with this minus P1 squared, and you just have P dot Q. But if you look at the mass shell conditions we had a few minutes ago, this is not 1/2 Q squared. So this term we can just throw it away, as similar to this term. And again, using the fact that P1 dot Q is 1 over Q squared, and P2 dot Q minus 1 over Q squared on the mass shell constraint, we can essentially neglect the distinction between P3 and P2, and a similar relation also for P3 dot P4. So effectively, here we can just trade the 3 for a 2, the 3 for a 2, and here 4 for a 1, and 4 for a 1. So the only non-trivial thing, calculate, say, 2 P1 P1. Now let me spell out this P, beta mu rho, beta mu sigma minus 1 over D minus 2. 2 P2 P2. And then 1 over Q squared. Plus, let's say, analytic terms in Q squared or short range. Let me write short range. No, yeah, short range after Q. The analytic will be. Finally, you have a factor of 4, and then an 8 that comes from here, so 32 pi g. And these contractions, using the definition of sigma, so you see we get P1 dot P2 squared, which is sigma factor of the masses, Very good. So now what do we do with this? We have to perform the Fourier transform. And let's see what we get. Then after that, I think we can take a break.
There is a problem. -1 over d over 2 summed to a tensor. So I'm confused.
Ah, thanks. Yeah, I suppose I forgot to write down the equal. Thanks a lot. It'll be like this, right? Thanks. Okay, so performing the Fourier transform using the formula I gave you earlier, we get this I A0 theta B. So the Fourier transform of this, which I'm calling A0, the three-level amplitude, is simply 2πg divided by well, I'm switching a bit between d and epsilon. I hope it's not a problem. So this, okay, this is dimensionless, as you can check. So in order to restate h bar, we can put an h bar here if you want, because this is gm squared, which is the dimension of an action again. And also let me introduce a symbol which is sort of suggestive. I'm going to call this 2i delta 0. And now, maybe 2 comments or 3 comments. The first one is that, okay, in order to just capture these long range pieces, instead of actually using the Feynman rules, we could have used some trick that will be actually useful at higher loops, which is instead of applying really literally the Feynman rules, we could have glued together 2 3-level amplitudes with just 3 external particles. So if we define something like this, apart of this factor, possibly a factor of I, this would be give exactly the same result, right? So this is a technique somehow called, sometimes referred to as generalized unitarity. The idea is that by cutting this line, you can factor the amplitude in terms of 2 lower point amplitude. And of course, you have a price to pay, which this calculation does not capture these short range terms, because this would not have this 1 over q squared pole. But this is fine because we don't care about that. In fact, similar strategy will be helpful as well do. The second comment, which is perhaps the most important, okay, now let's look at this prediction of expression that we got for the B space amplitude. And remember that, okay, this came from taking the Fourier transform of this S. So this will contribute to the S matrix in B space as 1 plus 2i delta 0 of B. And then in principle, we should consider higher orders in the perturbation expansion. But the problem is that this is proportional to gm squared over h bar. So this is of order, this correction here, so let's say 1 plus something of order gm squared over h bar, as you can see from here. And this parameter is very large. It's 10 to the 79, 78. So this is completely nonsensical, right? Because we are doing a 3-level calculation, which we hope to be small, right? In order to trust perturbation theory, we wanted there is a 1, which is the forward process, which is by far the most likely, and then we want a small correction, which is the 3-level, and then an even smaller correction at 1 loop, which here doesn't seem to be the case. So we cannot trust perturbation theory. And in some sense, the objection would have been made at the very beginning, right? Because the problem is that we have two dimensionless combinations of the coupling that enter the game. One is small, so we like it, but the other one is very, very big. So of course there is a risk that it will appear, and indeed it does, as you can see from this example. So the problem is that we have these large contributions around and we don't know what to do with them yet. This is going to be hopefully clear by the end of this lecture, but for the moment it seems to be a puzzle. It seems that we have to throw everything away, right? You cannot simply just not apply this perturbative method. And perhaps the last comment is that here you have an IR divergence. So if the epsilon goes to 0, This is somehow expected because of the long-range nature of gravity in the equal 4. The fact that these Coulombic exchanges are well known to have this sort of infinite range problem, but as we will see, this will not be a problem when deriving the predictions for the observables. So let me promise that this will go away later. Okay, I think we can take a break for like 5 minutes or so.
5
or 10.
10
Yeah.
because 5
Yeah.
10 minutes break. Just before the break, let me ask. So A0 capture also in your definition, A0P capture the short range, and the A0 tilde is just the leading term.
Yeah, exactly.
Is it this the?
Yes, if you want, you can even try to apply the formula I gave earlier to perform the Fourier transform and use it to perform the Fourier transform of a short range term, and you will find that it gives 0 just because some gamma function in the denominator. You remember there was a gamma of minus nu in the denominator.
Okay.
So I mean, in dim reg, this is literally 0 and nu is 0, 1. But yeah, so in the end there is no distinction here.
Okay.
For AT. But more physically, this means that we are neglecting short range contributions. I mean, there would be delta functions in B space that we are not writing down.
Okay. Are there some other questions before we stop for 10 minutes? No? Also in the virtual room, if you want to ask questions, you switch it on your mic and we will hear you. So, no sign of... Okay, so let us pause for 10 minutes.
Okay. So before the break, we left with this sort of problem that seems that the tree-level amplitude, when expressed in B space, is very large. So what do we do about that? And okay, I know many people already know the answer, but let's pretend we don't. So we just pressed on without despairing and try to see what happens at one loop. This will be the strategy. Now, of course, the one loop calculation is more challenging because if one were to approach it just by calculating all Feynman diagrams and calculating all the integrals of all these small times, it will be very long. So there are two ideas that have to do with this more modern method for scattering amplitude that can help us simplify the problem. So as I said, the problem can be sort of divided into two steps. First, producing the integral, so-called amplitude integral. This would be just a very complicated rational functions that come by summing all the Feynman diagrams according to the Feynman rules, and then performing the integral. In this case, integral because it's just one loop, but in general integrals. And these have, I mean, there are different strategies to attack these two bottlenecks. Let me sketch today, without going too much in detail, how what is a good strategy to obtain the desired integrand which is relevant for these long-range interactions, and outsource instead to lecture probably number 3 some comments or some more details about the issue of actually calculating the remaining Feynman integrals. So the idea is to realize the fact that this integrand is again, as I said, a complicated rational function which can be organized in a convenient way in terms of drawings, which are not Feynman diagrams. Let me so let me note with the thick lines, the two massive lines, and then with the thin lines, what will correspond to gravitons, but in a second I will specify in a moment. Oops, become too thick, also the intermediate line. And then bubbles. So these drawings simply represent rational structures, and the lines here represent their denominators. So in particular, the presence of a thick line upstairs means that there is the denominator associated to the propagator given by that line. But these were also attached with some numerators, which in general are non-trivial, and this is just a way of organizing the structure. It's not really a way of writing down how one calculates it. But this is useful because the denominators dictate the analytic structure of this rational function. And in particular, when taking residues associated to these denominators going on shell, the idea is that the amplitude must factorize into lower point amplitudes associated to the exchanges of the states that one cut, the lines that one cut, between the two lower point amplitudes. This lower loop amplitude. This is particularly simple in this case because our goal is to take into account these long-range contributions. And for instance, a drawing of this type, for instance, it is clear that will not contribute to our problem because I mean here the massive lines touch. So in fact, we can check that this is an analytic contribution in this two space because it's a short-range contribution. So actually, the only topologies that we care about are precisely the ones that I've drawn. So in which there are these two massless lines that can be cut, say for instance. And therefore, it's easy to check that in order to obtain this integral, it's enough to consider a single so-called generalized unitarity cut, which is the one in which one combines two copies of this amplitude glued together. Let me explain why. Let's see here. So the idea is that this amplitude, is an amplitude for a scalar and two gravitons, right? For the scattering of a graviton of a scalar, if you prefer. So sometimes it's referred to as a Compton amplitude, although of course here we are in gravity and not in electromagnetism. So let's say the gravitational analog of a Compton amplitude. K1, K2, K1, K2. And now the idea is that if one glues together, more precisely one sums over all the possible intermediate exchanges of helicities of gravitons in this way, between two blocks of this kind, since each block has the following representation in terms of topologies. Now let me try to do the exercise. We're going to try to glue two copies of this. So and then one below. So we literally have to just glue them as drawings in the result, of course. So here the twisted one is coupled with the non-twisted one, so we get a twisted box or crossed box. Here we have a similar thing. And then when the two twisted ones come together, we can actually untwist them, right, and get the upright box, let's say. And finally we have this. This can be twisted or untwisted freely because this you can freely. And finally, bubble. So as you can see, we get twice the integral that we care about. So the bottom line is that for our calculation, the integral construction is very easy. For the piece that we care about, it's actually just one sum. These two graviton cuts up to topologies that we don't care about. Now for this amplitude, it's very useful, for this sort of building block amplitude here, it's very useful to use a representation which satisfies the so-called word identity exactly. So namely, for instance, Q1 rho A T equal to 0 on the mass shell conditions, of course. And similarly for Q1 sigma, Q2 alpha, Q2 beta. And the reason for that, of course, is that here, when by this drawing, what I mean and that one should actually glue together, I mean, should sum. I mean, let me do it for one line, let's say that they should sum over the two polarizations, 1 and 2, of the two exchange gravitons. So there will be the amplitude with this polarization tensor, so it will be an epsilon mu, an epsilon rho sigma, and another one for the other leg, but again, it is schematic here. And the idea is that the sum over the helicities can be actually translated to this famous projector, so-called TT projector, which is I mu rho, I mu sigma, I mu sigma, I mu rho, minus mu over d minus 2, I mu mu, I sigma, and factor 1/2, where pi is defined by eta mu mu plus lambda mu, say k, this is the momentum we are interested in, k mu plus lambda mu k mu, and lambda dot k is equal to minus 1, lambda squared is equal to 0, and this is equal to k squared in the sense that we are on the cup, right? So really these are now on-shell momenta. So you see the simplification that you get if the amplitude satisfies this nice identity is the fact that whenever you find a k or a q would be in this case contracted with either amplitude, you can simply throw away that contribution, right? And therefore this structure you can simply replace it with a constant, in particular k and lambda independent structure that we had a few minutes ago in the London propagator, right? So this is why somehow this is a way of exploiting gauge invariant in order to make your life as simple as possible. Otherwise, we would be forced to consider an integral that also involves this additional reference vector lambda, is projecting away the longitudinal modes. Otherwise, in this way, the longitudinal modes simply go away on their own, and you can just include them. So this is a technical remark, but you see now the pipeline is very simple. You take this amplitude here, which is a 3-level amplitude, you plug it in this cut, you find the integrand just by contracting all the indices here with this structure P, and you find your the rational function that you have to integrate, and then we will discuss in a couple of lectures how to actually perform these integrals. The only thing that I have to give you is the amplitude, the constant amplitude. Let me perhaps write it down here instead of this. It's not really important, but I wanna give it for completeness. Maybe let me write it down here instead of the topology. Of course, I mean the expression is highly non-unique, but this is one expression that satisfies this identity. Then let me introduce some rho, some gamma, which repeats twice. So convenient rho alpha, P1, Q1, Q2, gamma, sigma beta, K1, Q1, Q2. And each of you guys is given by K1 plus Q2 rho, K1 alpha divided by Q1 dot K1 plus Q2 minus K1 plus Q1 alpha K1 B K1 rho, sorry, divided by K1 dot Q1 plus beta rho. And you can check as an exercise if this satisfies this identity. For instance, it's obvious when we contract with the Q1 row, because simply this numerator cancels this denominator cancels this denominator, and we end up with K1 minus K1 minus Q1 plus Q1, because we contracted with Q. The other one, so contracted with Q2 alpha, is a bit less trivial, but you can check it by using the equations of motion. Sorry, the mass shell constraints in particular. Remember the fact that K2, which has been eliminated from this, which will be the momentum of the massive leg on the bottom right, is equal to minus K1 minus Q1 minus Q2, Q1, Q2. And then you can square both sides of this relation to obtain a constraint that links the quadratic combinations, in particular K dot K1 dot Q1 plus Q2 plus Q1 dot Q2 is equal to 0. Because K1 and K2 have the same mass, and the Q1 and Q2 are massless. So this is using this constraint, it's easy to check also the other one. I leave it to you. Oh, very good. Now, having sort of sketched, any questions on this sort of?
This in this notation QI, you sum over I.
Sorry, let me get the expression. Sorry.
So for the quantum amplitude, so you have QI dot something.
No, sorry, it's a 1.
Ah, dot. Okay, sorry.
Apologies. Yeah, I have the bad habit of writing 1 like this and not like this. So, yeah, it's a dot.
Okay.
Yeah, apologies. Okay, now that I sort of not done it in front of you, but kind of explain. I should have done the same also for this other thing. Okay. Sorry about that. Well, I guess the only part is not really visible is ether. Okay. Anyway, so this is the idea of performing the calculation. So now let me maybe give the result up to one more justification that I wanted to discuss, which has to do with unitarity. So the reason I'm using the blackboard in a sort of erratic way is that I wanted to keep this delta 0 here. Maybe let me erase this part. So even without doing the calculation, we know that the one loop amplitude also satisfies a constraint that is due to unitarity of the S matrix. We will see more in detail one of the next lecture what the consequences are, but well, expanding this one gets that minus I t minus t dagger is equal to t dagger t, and then the idea is that taking a matrix element of this identity and inserting a complete set of states here, one can derive relations among what is essentially the imaginary part of an amplitude in terms of integrals over phase space, sums over phase space integrals of lower loop amplitude. In particular, what is relevant for us at the moment is that the imaginary part of this 2 amplitude is a blob. This guy is equal to 1/2 the in principle, one has to sum over all the possible ways of inserting the the intermediate states. So there is a 2-particle distribution, which essentially is going to be this as a drawing, plus higher order contributions that for the moment they are not important because they only enter at higher loops. So here, what I have to do is I have to write down the measure for this phase space integration. So let me pick an orientation for the loop momentum. So this is going to be P1, this is going to be L minus P1, and similarly, this is going to be P2, and this is going to be L plus P2. So the measure I want to write down, I guess, is and then we have a product of 2 4-point amplitudes, which are the same as the one on the right. One with a momentum transfer L, and the other with a momentum transfer U minus L or L minus U, which is the same. Tau, because here we have the T dagger. So for us, since we are at one loop, what we can deduce is that the imaginary part of this one loop amplitude is 1/2 the integral in which we can just put the tree level, right? And moreover, since eventually we're going to take a Fourier transform with respect to Q, and Q is small in the sense that we discussed, again, it will be a simple application of the method of regions that we discussed a couple of times to check that the only relevant region for this integration in L is the region in which also L is small and of the same order as Q. So again, here I will be able to neglect this L square to leading order up to this subleading 1/p correction that we discussed a couple of minutes ago. So to leading order, what we have is that the imaginary part, well, let me adopt a notation. No, sorry, for one more time. Again, Q minus R1 minus Q doesn't play any role. That's relative corrections that are suppressed by 1/b squared after Fourier transform with respect to the leading order. They are suppressed by Q squared with respect to this leading order. So I guess what I'm trying to say is that even without doing the calculation, we know that the total amplitude must be given by this imaginary part plus a real part. And the actual non-trivial content of the calculation, as you can see from this formula, is just the real part, right? Because the imaginary part, you can just deduce it by performing this phase space integral. Then there is a further simplification that the real part, I'm going to write it down because you have to do the calculation in order to get it. But the imaginary part will be simpler. We will see in a second. So yeah, in fact, here there are also higher cuts. The real part, let me get the factors right. Of course, here at one loop, everything is very easy to calculate in generic V, but let me write it down in D equal 4 for simplicity. 2 pi G squared, M1 squared, M2 squared, 3 pi sigma squared minus 1 over Q. What you want, square root of Q squared. Okay. Now, what happens when we go to impact parameter space is the following. That, as you can see here, this phase space integral looks quite a lot like a convolution. And indeed, what happens is that the Fourier transform diagonalizes that convolution to leading order. So the statement is that now we're going to calculate a tilde of B, and this is going to simplify the first line. Let's see how. So let me try to do it. So this is left, sorry, without any I, less related. And then there is an exponential somewhere, yeah, here. So now the idea is to redefine Q, say as Q goes to probably N minus 2, for instance. Let's see if I got that right. So now you see what happens that in okay, here I will get something that is evaluated at Q or minus Q, which is the same for the tree level amplitude, 2 to 2 tree level amplitude, and here something that is again evaluated at L. The only possible issue would be the delta functions, right? Because here this depends on Q, this depends on L, and when I substitute here Q that goes to L minus Q, I would in principle get something that is like this, right? But now what I can do is that I can use the other delta function, which tells me that P1 dot L is 0, to notice that this substitution doesn't do anything in this delta function. Of course, another way of doing this is just to go to a frame where this delta function has been solved, and therefore there is actually no longitudinal component to begin with, but I think this is a sort of cute way of seeing it without ever specifying a frame. So the bottom line is that I can do this redefinition, and then the integral clearly factorizes as follows. Well, okay, let me not rewrite everything. There is an a tilde 0 and another a tilde 0, right? Star. In principle, it would be star, but this is actually real. So there is no I here, so this is actually a real function, so there is no need to put a star. Plus the real part of a tilde 1, which now I'm calling P delta 1, reason to be again be apparent in a second, plus higher order in B, in particular suppressed by 1 over B squared, you remember, with respect to the leading order. But a tilde 0 is this delta 0. So now let me write 1 plus IA 0 plus sorry, a tilde 0, a tilde 1, and plus the guy over there, I delta 0 plus 2i delta 0 squared divided by 2 factorial, okay, plus 2i delta 1 plus things that are suppressed by 1 over b squared with respect to this leading order, let me call it big delta 1, plus things that we haven't calculated because we have to go to 2 groups, etc. So again, just to have in mind the scaling, this is roughly scaled like b to the 0, or more precisely b to the 2 epsilon. So let's say b to the, I mean, it would be log b actually, but in b equal 4. But let's say b to the 0, so 1. This also scales like 1, this scales like 1 over b, and this instead like would scale like 1 over b squared. Okay, so finally, I want to give you the expression for this delta 1, and then we can discuss the structure that has appeared, which starts now to be rather clear. IG squared 1 and 2 divided by 4. You want h bar, reinstate it once more. Sigma squared minus 1, and then the same multiply by sigma squared minus 1, and 1 plus. In d equal 4, of course, again, it's easy to calculate in any dimension, but. Okay, so now that we got here, finally we can see what is happening, right? Hopefully. See what is not in the way. So we saw that there is an imaginary part which actually factorizes basically thanks to unitarity, and it gives us precisely the same structure that we had at 3 levels, squared divided by 2. Put factorial in order to make this even more suggestive, but I mean, I guess you all got the point that this is sort of suggestive on an exponential, and indeed, what sort of highlighted in this bottom-up presentation that we have today goes on. So indeed, the pattern goes on also at higher loops, and one can in fact prove. There is in particular a paper by Kabat and Ortiz, where they prove the fact that the leading order in this classical limit of the L loop amplitude, if you want. Really, the leading order, so the most singular in this large ratio GM squared over H bar is precisely well such that, let me say, leading in GM squared, so such that this delta 0 exponentiate. And in fact, there are also further results concerning also the exponentiation of the terms that involve delta 1, small delta 1. So the first leading correction over here particularly by first by Curry, Sterman, and more recently by Bierumbone and collaborators. And but essentially the key idea is that, let me maybe use the space I have over there. That when written down in impact parameter space, the amplitude exponentiation according to this exponential, and then possibly there can be non-exponentiated terms which are suppressed by these powers of h bar, particularly the first instance is this big delta one, which are again suppressed in the classical limit but are important in general. And now we are in a position to rediscuss this issue of the large ratio, right? So in a sense, the problem was the fact that we were looking at the wrong quantity. We were looking just at the expansion, at the loop expansion of the amplitude, but this is not an object that has a nice classical limit. And the reason is that order by order in perturbation theory, you will have pieces which are singular in this gm squared over h bar, and then if you go on, they will be even more singular. So you see, this is even more dangerous. Sometimes people call it, since usually this is called classical, sometimes people say super classical, but in a sense this is simply nonsense due to the fact that you have expanded something that is very large. So the right thing to do is to resum first, and then the object which does have a nice classical expansion is this exponent here, delta. There's delta 0, delta 1, and then in a second we will write down delta 2. And you can see this indeed to read it mean the overall scaling is this gm squared over h bar, but then, okay, here there is a log. And then you can check by comparing the expression over here with the expression over there, that although this has an overall gm squared over h bar, then it's further suppressed by the power of gm over b. So this is an object that has a nice pm expansion. If you want it homogeneous in the classical limit, there is a 1 over h bar in front, and then it has a nice expansion in the pm limit, which is, as you can see, controlled by the small post-Minkowskian parameter. If you want, this is reminiscent of what we do in WKB, right? We all know that the right way of expanding the Schrödinger equation in the classical limit is not just to look for a power series expansion, but it's to look for an exponential form, in which the exponent essentially is the classical action divided by h bar, and this is, well, exactly what happens also here. Another comment is that really just the leading exponentiation is very suggestive, because you remember we deduced this delta 0 just by looking at a single three-level exchange. But now what we are saying is that actually looking at all order in perturbation theory in order to obtain the leading behavior, we have to look at all the ladder exchanges and possibly also cross ladder. Dot, 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 dot. So in a sense, once we have identified the right building block, we can just iterate it in order to get the right resummation to all orders. And then from this exponentiated form, which, as you can see, sort of intuitively resums all orders in these ladder exchanges, we recover the right classical limit. So in a sense, this makes precise the notion that classical gravitational interaction is mediated by the exchange of many gravitons, not just one or two, as in the typical perturbative calculations, right? Okay, maybe one last point, and then I will stop for questions. This is a nice sort of observation, but can we also make it useful? Is it also useful for our original goal that was to calculate some observable quantity about the classical process? I mean, this is a nice property that the amplitude has in B space, but what do we do with that? And the idea is to invoke a saddle point approximation, more precisely a stationary phase approximation. So now that we know that the amplitude in B space takes the form of an exponential, we try to go back from impact parameter to momentum space to perform the inverse Fourier transform, if you prefer. And then you can see that since this is very large, the integral must be dominated by the stationary point of this exponent, which fixes for us the classical impulse to be just a derivative of the iconal phase with respect to the impact parameter. And then by taking this derivative in the two formula that we have over here and over there, we can finally get the first predictions for gravitational observables that I was sort of advertising at the beginning. Let me write them here, perhaps, and discuss them. So Q would then be something like B mu or B, and then it will be Q1 PM, Q2 PM, so 1 PM meaning order G, 2 PM order G squared, Q1 PM is 4G and 1 and 2, sigma squared minus 1/2 divided by B square root of sigma squared minus 1. And you see, as promised, the issue with the infrared divergence that we had over there has gone away. And the reason is that when taking the derivative with respect to B, you pick up an epsilon from the derivative of B to the epsilon that cancels the infrared divergence and leaves behind this finite result. Or if you want, expanding for small epsilon that quantity over there, you see that the leading order, the divergent part is actually B independent, right? So then when taking the derivative with respect to B, the divergence goes away. So if you want, it doesn't introduce any problem. And Q2 PM is given by the derivative of the thing over there. So 3 times G squared. Divided by 4B squared. Okay. Any questions?
I'm a little confused by the origin of capital delta. Well, in the one loop, it contains the correction, the many body correction.
No. The many body correction only contributes to higher loops because by power counting, you see this. If you put here the 3 level, you get G times G, so G squared, which is the order at which we are at one loop. But anytime you put a higher point amplitude or more cut, you would get higher power. For instance, if you put the 3.223, you would get G to the 3 halves times G to the 3 halves, which is G to the cube. So this is actually important for what I wanted to flash before concluding today, which is the 2 loop case. But no, here it involves this dot dot dot. So higher order corrections in 1 over B, or more precisely 1 over P times B, to the amplitude at 2 loops, yeah. Or to the Fourier transform. Because you remember we had this issue. For instance, here, if I were, instead of taking a tilde, where did I do it? I guess I already erased it, but instead of taking the tilde of this expression, I were to take the ft, so remember the one with the full delta functions, then this would induce some corrections that precisely modify this big delta, if you want. So actually, I wanted to spend a few minutes on that in one of the next lectures when discussing unitarity, because this is one of the subtleties essentially at higher order.
Yes. So before using unitarity, you were saying that by doing these 3-level amplitudes, we can get, but then and then later you decompose into real and imaginary parts. So by doing this procedure, do we get both?
Yeah, these are two distinct procedures in a sense.
Okay.
One procedure is you just calculate it. You sit down. I'm not doing that today. You sit down and you glue together these two Compton amplitudes I gave you, and you find an integrand, which is just a rational function. Then you have to decompose it into some integrals that you know how to do. We'll discuss them a bit in a couple of lectures. And then you find the result, which involves both the real and imaginary part. This is the systematic procedure. Now, for today, as a sort of a shortcut to show you some structure without actually doing the full calculation, I invoked unitarity to actually show you that, for instance, the exponentiation of delta 0, so this delta 0 squared divided by 2 factorial actually can be, even without doing the full calculation, can be checked by this unitarity argument. Otherwise, you can just do it. And in fact, in a sense, this exponentiation is a sort of constraint to for your calculation, right? If you had some mistake, you could find the wrong factor in front. You could have 1/3 instead of one half, and then you know you made a mistake. But they are two sort of independent. Instead, for the real part, you have to do the
Yeah, for this was asking for. So for delta one, you would need to do something like this, but I guess you could throw away imaginary part or something.
Exactly. Then the issue would be, in this case, it's very simple because the imaginary part and the real part seem very well separated. For instance, the two loops, the issue starts to become a bit less tricky, although it has been discussed exactly along the lines as you say. There is a way of directly throwing away these sort of iterations. So maybe I will come back to this in a bit. So then the last comment I wanted to make before splashing the two results, or maybe we can do it next time, is okay, then I was promising to actually go to this deflection angle, so which is just related to Q by these simple trigonometry considerations. So let me write it down maybe somewhere, and then comment on the two limits. Go back to the things we said at the beginning. We do a calculation, but then we have to check whether in the regime that agree with other calculations we have agreement. By the way, these results for the impulse or for the angles were already obtained long ago without using any of these amplitude machinery. Particularly the leading one, I think, was already in the 50s in papers by Bertot, and also the one at 2 p.m. by Westphal in the 70s, I think. So using that relation, which to leading order simply means that theta is q divided by p, because we can expand for small theta. We are in a small deflection angle regime, as Lenin was also saying. We get theta 1 p.m. simply for g, the energy, times sigma squared minus 1/2, divided by b times sigma squared minus 1. And theta 2 p.m. is equal to 3 pi g squared and 1, 2, the energy minus sigma squared, sorry, the energy times the 1 plus m2 times sigma squared minus 1 divided by 4b sigma squared minus 1. So here I'm using that identity E times B equals to 1. Okay, so now one issue would be, can we compare with some regimes, right? Sort of the power, the useful thing about this PM expansion is that we have a parameter sigma which we can dial up and down. So let's discuss that. So let me first discuss the ultra-relativistic limit, which is sigma going to infinity. Now, of course, in gravity, we cannot just send the velocity to infinity and keep the impact parameter fixed, because otherwise, since gravity couples to the energy, if we send the energy to infinity, of course, the result will be infinite. And so the right way of taking this limit is to also make b very large, such a way that GE over b stays fixed and small. Right, because E, of course, increases with sigma. It's m1 squared plus 2m1 to sigma. So in this limit, theta 1 pm, as you can see, these two powers of sigma squared simply cancel out, and we end up with 4GE over B. And instead, theta 2 pm is not so lucky in a sense, because here these two things cancel out, but then there is a power of E. In order to make it GE over B squared, we have to multiply and divide by E. So apart from a numerical factor, it goes like GE over B squared times the ratio between the mass and the energy. So this goes to 0 instead. And this perfectly agrees with the results that are actually available for the massless case. In particular, there is a famous paper by Toft about gravity dominance in shockwave scatterings, where people have discussed the scattering of shockwaves. So when the two objects are massless, onto which indeed this limit should match, right? Because if the energy is so big that the masses are negligible, then the result should be intuitively the same as the one of massless object. So this agrees with the, let's say, Toft result, and this is 0. And the reason why it's 0 is that in fact all even PM orders are thought to be 0 due to the fact that there is well, the expansion of the integrals is analytic in q squared over s, which, as you can see, brings 2 powers of q or 2 powers of 1 over b with respect to the leading order. So here there is no mass with which to build a combination like m over q, for instance. So since the leading order in this icon exponentiation is delta 0 squared, the next to leading order would have a square root of this, right? I mean, just one order subleading, but this is this is not, one cannot build one such contribution, and therefore it vanishes. So expect it. And what about instead the post-Newtonian limit? So when sigma is equal to 1 over b squared is equal to 1 plus, I guess, 1 half b squared plus dot dot, so v is going to 0. So to leading order here, we just get, I guess, a factor of 2. Sorry, probably was someone. So 2gm, m being the total mass, over b squared. And yeah, the 2pm is 3 times b squared m squared over b. So now it's sort of interesting because it illustrates what I was saying at the beginning. As I was saying, we are supposed to check with the post-Newtonian expansion. So we have to identify at which order in the post-Newtonian expansion these contributions to deflection angles appear. And you remember in the Pn expansion, the counting is that gm over r or gm over b is of the same order as v squared, right? Because both parameters are small at the same time. Although here we are re-expanding for small g over b, of course. But, so the idea is that powers of g count as much as powers of v squared. So here, as you can see, this is of order 0pn, or if you want a contribution to the Newtonian angle. Instead, here we have 2 of these and only 1 of these, so this is of order 1. And you can check indeed that, for instance, in the paper by Binda, Moore, and Radico, where these are ability goes to much higher orders, these are perfect agreement. So here is one comment I wanted to make about this complementarity between the Pn and Pm expansion. You will perhaps remember from your one of your elementary courses in bachelor that, well, we all do a calculation of a deflection angle in the Newtonian potential, usually when discussing Rutherford scattering, for instance, but maybe some other also analytic mechanics course. And the Newtonian angle that we derive is actually much more complicated than this. It's not just 2gm over bv squared, it's twice the arctangent of gm over bv squared. So, how come? But you remember, here is really why I was sort of stressing the difference between these two scalings. Here, this is really derived in the regime in which gm over b is of order v squared, and both are much smaller than 1. And you see, in this regime, you cannot expand this arctangent, right? Because this is an order 1 parameter. It contains information, if you want, to all orders in this parameter, but to leading order in v. Instead, what we are doing here is that we are really expanding for small g. So from this, we only get the leading order of the re-expansion of this guy over here. So this is a particularly bad example of how to compare the Pm and Pn, but it kind of instructs because that's what we in practice do. Also for more complicated observables, for instance, for the waveform, you calculate something in the Pm and then we compare with the re-expansion of the Pn. Actually, there are also techniques that allow, for instance, given this angle, to reconstruct the whole 0Pn. But the idea there is to go through a potential. So the idea is that instead of directly trying to guess this from this, which is very hard, could be a sine, could be any other function whose small argument expansion, the argument itself, you fix an effective description of the problem in terms of a potential, recovering the Newtonian potential, in fact. And then you actually redo the calculation that one would do in elementary courses, so to derive the angle from the potential. And in this way, one can actually reduce the full thing. In going through the potential, the idea is that, so maybe we conclude with this today, or if we have more time, we can flash the next topic, but it's not necessary. So the potential is a bit nicer in the sense that there are no inverse powers of v squared, which would be the idea why the potential is simpler. So, but you see, you have 1 pm, 2 pm, and so on, and then you have 0 pm, 1 pm, etc. And so this is the order G. So Gm over R would be, right, the usual Newtonian potential. This is over Gv squared, and then there are other contributions, and the 2 pm starts again at G squared without any inverse power of the velocity. So you can see in the potential you can indeed recover the full 0 pm by knowing the full 1 pm. But this is not important directly for the answer. You have to go to the potential. Okay, any question on this? Okay, so I understood from Ricardo that it's okay to keep you until like quarter past or something like that.
Yes.
So then maybe I can, of course, I will not do any calculation for the two loop case, but I wanted maybe to write it down just once the lecture, just to show the structure and comment a bit on the properties. Okay, now to go to next order, and then going to lunch. Let me reiterate again. So the main message is that when written down in terms of impact parameter, the 2 to 2 elastic amplitude exponentiate in this form. And in practice, how we do use this relation? As I try to illustrate at 3 level and 1 loop, we expand it, because in practice we only know how to calculate the perturbative amplitude. So of course at 3 level we just get the 3 level amplitude in bit space is the iconal phase at 3 level. Then we have this exponentiation terms plus the first correction plus this first quantum remainder. And then if we go to the next order, of course, the structure will be the following. We have y delta 2, the first sub-subleading correction to the phase. And then in principle we can go on, but let's stay here. So you see the idea is we calculate the 3 level, we determine delta 0. We calculate the 1 loop, we check that there is an exponentiation of delta 0 at the order b to the 0, or more precisely log b, because when we expand for small epsilon, of course, 1 over b to the epsilon is log b. Then we determine this. And this we determine after checking exponential on this, and also we determine this. And then at the next order, we check the exponentiation of delta 0 and the exponentiation of delta 0, delta 1, and use the previous data to determine delta 2 and potentially delta small delta 2 and potentially capital delta 2. But you see this at next to leading order, and then the way we distinguish this is just by their scaling in B, right? So this is order 1 over B, and this is the order 1 over B squared, including delta 1, order 1 over B squared. So you see that the tricky point, and the reason why I emphasize that one has to be careful about this delta 1 and the definition of the Fourier transform, is that now there is an interference term between delta 0 and delta 1 that we have to subtract before identifying what is at order 1 over B squared with delta 2, right? Otherwise, we include something that should not be included. And up to this subtle, the result is the following. So the two loops, there are several new features that appear. There is, for starters, the delta 1 is a real and an imaginary part. I will comment on this in a second. there is a piece which right in the first line, separated from the rest for a reason that I will get to in a second. And I have some. And I think the parenthesis ends here, and then there is something that I will call and first let me write it all down, and then I will comment on it step by step. Sigma squared minus 3, sigma squared minus 1 and sigma r cos. And there is also an imaginary part, which I'm not writing down fully, but I write down a piece that is important and will come back in later lecture. Times the real part. Okay, sorry, there's a lot to take in at the same time, but hopefully I will try to break it down now. Please tell me if it's not visible, because I realize that there is a table a bit here.
You can.
I have a question.
What? Yeah, it's the Van invariant test. Sorry. Yeah. So, so the first line, as you can see, has a bit of a different structure with respect to the masses. And in particular, it involves the terms that are of highest order in the mass ratio. You remember this quantity we introduced. But if you want two leading order, for instance, if you send M2 to 0, this will have the highest power of M1. For instance, we'll have a term which has M1, while the others will be smaller, right? And in the, sorry, well, M1 divided by M2, of course. So this is why it can be determined by the probe limit. So this you can actually deduce, at least the coefficient in front and the structure in terms of sigma, etc. You can deduce it by just looking at the geodesic in Schwarzschild background expanded for small g. Then the next order are the so-called potential contributions, which are actually non-trivial in the sense that they are not determined by the probe limit. And as you can see by the powers of M1 and 2 in front, squared. So these are, in a sense, the first result that was obtained by means of this amplitude method that had not been obtained by, looks so short, had not been obtained by GR techniques. It was the great achievement of the collaboration by Slyburn and several other people in the US in 2019. And this is really the effect of the gravitational pull that each black hole feels due to the presence of the other one, in which both objects are really dynamic. So you cannot just approximate one of the two as being a heavy one and the other to be light. And then this last line here is instead a dissipative effect. It goes under the name of radiation reaction. And it's really an effect due to the loss, in particular, of angular momentum that each object experiences due to the interaction with the gravitational field, which then causes the trajectories to bend a little bit. In particular, if you take the derivative with respect to b, as we saw, and calculate the corresponding contribution to theta, you will find that theta 3 pm has some even in velocity contributions that come from the probe limit and potential contributions, and then they have some odd in velocity contributions that all come from the radiation contribution. This is a case in which essentially, I mean, the first case in the perturbative expansion in which also the dissipative effects start to show up. And finally, okay, I realize the last line is poorly written. Is it readable? Yeah. More or less. Anyway, the idea is that this radiation reaction part, for a reason that we will hopefully discuss in the next or one of the next lectures, is actually proportional to the divergent part of the imaginary part of the icon. Or if you want, as you prefer, as you probably know, these divergences always come with a partner logarithm, if you want. So the reason, as we will see, is that this logarithm by unitarity translates from a piece in the imaginary part to a piece in the real part, and has this simple form. I mean, this form here in terms of our beloved parameter sigma. In a sense, this is the really difficult part of the calculation, as you can see, because it's a bit like the real part in the previous order. Right? You have to do the calculation to get it. This dissipative part, instead, you can deduce it from this imaginary part, which in turn you can deduce by unitarity, and in particular the divergent part you can further simplify it by using soft theorems, but again, we will discuss it more in detail in one of the next lectures. The last comment I wanted to make before concluding today is again about the limit. In particular, let me focus on the high energy limit. And then we can all go to lunch. So theta 3 p.m., or well, maybe even let me just discuss it at the level of delta 2 without taking the derivative. So one can check that in the ultra-relativistic limit, this real part of delta 2 is smooth in the sense that it behaves more or less like the free level. So if you have some GS, is our beloved GS over H bar if you prefer, times theta 1 p.m. squared over 4, with theta 1 p.m. given by that guy over there in the ultra-relativistic limit, of course. And this is in perfect agreement with the results obtained by Amati, Cefaloni, and Veneziano in 1990, again studying the massless problem. So they managed to calculate the icon at 2 loops for the massless case, and now this result agrees in the limit with theirs. Notice that there is a non-trivial cancellation when taking this limit between this arc cosh in the potential part and another arc cosh in the radiation reaction part. And in fact, a few years ago, this was a bit of a controversy in the literature. Eventually, this was the resolution, but somehow the idea is that the 2 loops, this icon is well behaved, and therefore also the deflection angle is smoothly connected to the massless case. Notice in principle this is not completely trivial, right? Because the scaling we had discussed at the very beginning involved the masses in a trivial way, and also this is this warning that I sort of placed in one of the points of the introduction, that is not always guaranteed that this works. And in fact, we will see also already next time an example of an observable that is not that much. But okay, for the 2-to-2 case, one is lucky at 2 loops. So for today, I guess we can be content with this. Thank you. Another important comment that I always forget to make is that not only it's smooth, but it's also universal in the sense that, for instance, if you were to do the same calculation in terms of supergravity theory, provided that there is no other massless particle with spin 2 or higher, then since the gravitational exchanges dominate at high energy, because they couple to the energy with the highest power in the final rules, they actually all reduce to this. So for instance, you do the calculation in any college supergravity, and it's exactly the same universal ultra-relativistic limit. Questions?
So can you tell us a bit more about these you called quantum corrections? So among approximations, I guess there are 2. The one is that when we do Fourier transform, and the other is this maybe it's a distinction between quantum and classical, or they're the same. I'm a bit confused with this how should I think actually about this delta one?
Right. So the idea is that the classical bits are the ones that are important for this exponent, because then the derivative of this exponent that gives the classical deflection angle. And I mean, here the counting of h bars is easy because delta goes like 1 over h bar, b m squared over h bar. And then when we take this derivative with respect to b, it's actually h bar, right? B dB. So then this goes away, and that's the reason why we end up with something that, well, if I had to raise it, yeah, as you can see from there, right? As promised, I made this comment at some point. Promised this is proportional to gm over b. Here there are no h bars, right? So this is really the classical deflection. Then, of course, one you could say, the amplitude contains pieces that are further suppressed. For instance, we were saying this is further suppressed with respect to delta 1. There is a big delta 1 which goes like 1 over b squared, right? Whereas small delta 1 goes like 1 over b. So actually this is 1 over b times 1 over pb h bar, if you want. So this is a relative h bar, an extra h bar compared to delta 1. What happens if you include that here, right? Who tells you to call this capital delta 1 and who tells you to call this small delta 1? Just include everything instead of small delta 1. Why not? It's just a reshuffling of this writing. What happens is that when you take the derivative, these things will not contribute to the saddle point because they are order 1 contributions to the exponent. They are not large. And even if you included them, they would have a suppression which is proportional to this parameter. So ultimately of order 10 to the minus 70, whatever. So they don't matter. The terminology here is motivated just by this exponentiation structure and by how they match on the observer.
But is it related to the fact that we are considering only non-analytic pieces, long-range pieces, or?
Yeah, in a sense, this would still be long range, right? Because they are suppressed by 1 over b, but still, it's a power law behavior. It's really their magnitude. When you write down the length scales together, that tells you that they're very, very small. And also, I would say that the saddle point approximation would not be very well justified. You want to apply them also to that piece because, it's an order 1 piece, so it's not really supposed to. We will see a different perspective on all of this next time when going through the KMOC strategy, in which, as you will see, all these ingredients enter in a different way. So, for instance, here the way in which we got rid of this problem of the GM squared over h bar large contribution is that we exponentiated them, and then they are not appearing in the observable. In the KMOC, or observable-based calculations, what happens is that they appear at intermediate stages, but whenever you calculate an observable, they actually vanish order by order in perturbation theory. So we will see that they will appear at some point, but they will just go away. So there is no need to exponentiate them even if you don't want to. And even the quantum pieces, of course, they are there in the amplitude, but they are simply much smaller than what you're interested in. And also another way of, say, going to the classical limit instead of doing this exponentiation, and then the saddle point is going to be that we have to introduce some wave packet, and then we have to invoke at some point in the calculation the fact that the shape of the wave packets is not actually important because they are sharply peaked around some classical value that we care about. But again, I would argue that this is only trustworthy when you look at the actually classical classically sizable piece of the answer, because otherwise interference effect with the shape of the wave packet in principle could be important, I think. So yeah, this could be another perspective.
More questions? Online, do you have questions? Okay, if not, thank you, Carl. And we stop here.